So now we're going to move on to the idea of specific types of distributions and probability density functions, and the one that we're going to cover first is called the normal distribution. And you may have heard of this before when talking about bell curves and whatnot for statistics associated with exams in your classes. But it's all based on the normal distribution, which is the most important and most widely occurring distribution in statistics. And so it's generally defined or a continuously random variable, and continuous random variable in this case is instead of discrete points, it's continuous along a curve, is normally distributed with parameters of mu for the mean and sigma for the standard deviation if the PDF of large X is the following equation here. So now what does that actually look like? So this is an example of what a normal distribution would look like. Again, it's no different than the other distributions we discussed in the previous video. The y-axis is the odds of a particular event occurring, and the x-axis is just the values of certain events. So for this one, for example, the mean occurrence is 0, which is why it's at the peak here, and the standard deviation is 1. And so one important characteristic is that all normal distributions share certain characteristics. Regardless of what the mean and standard deviation are. And the first is that for any normal distribution, 68% of the area under the curve, or the AUC as it's described here, lies within one standard deviation of the mean. So if the mean here is 0 and the standard deviation is 1, between -1 and 1, so 68% of the area under the curve. Within 2 standard deviations of the mean is 95% of the area under the curve, and within 3 standard deviations of the mean is 99% of the area under the curve. So this is the same plot as you saw before, a normal distribution with a mean of 0 and a standard deviation of 1, and this part is just meant to be instructive of how the shape of the curve can change depending on how these parameters of mean and standard deviation can change. So if I were to increase the mean from, say, 1 to 3, if this is what it looks, or sorry, the standard deviation from 1 to 3, if this is what it looks like with a mean of 0 and a standard deviation of 1, again, the blue is the y-axes have had to change to, or the x-axis had to change to fit everything in, but the curve in blue is the distribution we saw before with a mean of 0 and a standard deviation of 1. But if we change the standard deviation to 3 from 1 and keep the mean the same, you can see how the shape of the distribution changes. All the values in the distribution are not so nicely clustered around the mean of 0 and appear to be more spread. So that's why when you hear that a standard deviation of a data set increases, you'll be able to begin to see in your mind's eye, if the data is normally distributed, that you have more of a spread there. So if we go back and look at the example from the previous lecture regarding the heights of people in a classroom, you can begin to see that we could actually fit this to a normal distribution, and it looks fairly normal, right? There's a peak and it kind of makes a bell shape to it. So again, this is just meant to illustrate how the normal distribution is pretty ubiquitous in all forms of research. So, becoming more specific from the normal distribution, we'll discuss the standard normal distribution. And so this is born out of the fact that the equation that was presented earlier, the probability density function, or the PDF of a normal distribution, cannot be integrated analytically. And if you remember from the previous lecture, the ways in which we calculate probabilities of events occurring in a data set is taking the area under the curve. So if we can't integrate it, we can't calculate these probabilities. And that's true for analytical integrations, but normal PDFs can be numerically integrated in one case, where the mean is 0 and the standard deviation is 1. And that is called the standard normal distribution. We denote it as f of big Z. And the PDF that I showed you before simplifies to this equation here. And so when we call it f of big Z, you get this equation right here for describing a standard normal distribution. And that's a distribution with a mean of 0 and a standard deviation of 1, much like I showed you in the previous plots. And so with this, we can actually calculate probabilities. And so the trick going forward is, how do we take things that don't have a mean of 0 and a standard deviation of 1 and transform them to a data set where that is the case. So we have to apply what's called a change of variable to make non-standard normal distributions standard normal distributions. And so we'll substitute the following equation into a normal probability density function to get a standard normal distribution. So we'll basically, for a set that has a mean of a value mu and a standard deviation of sigma, we're going to take our data set, which is, if it's a random variable, big X, and we're going to subtract all those values from mu and then divide it from the standard deviation, and that will give you a standard normal distribution. There are proofs for this. It's outside the scope of this discussion, but believe me when I tell you that if your data is normally distributed and you apply this change of variable transformation, you get a standard normal distribution. And we'll go over this in an example in a minute. So it's also, again, just to reiterate, if big X has a normal distribution with a known mu mean and a standard deviation sigma, then this Z transformation has a standard normal distribution. So if this Z value has a standard normal distribution, then we can begin to make some definitions for example, the probability that a random variable X is less than some threshold value A now is represented by this Z statistic of A minus the mean mu over the standard deviation. And since the area under the curve for these distributions is always 1, if you wanted to go the other way and say what is the probability that a random variable large X is greater than A, you could do 1 minus what we have above. And just for the sake of completeness, if we wanted the probability that a random variable X is between A and B, we could apply the Z transformation to find the value of B and A and subtract them from one another, just like we saw in the previous example. So this will become a lot clearer when we do an actual example of a standard normal distribution. So here's our example. It is known that the resting heart rate of the Duke community is normally distributed with a mean of 70 beats per minute and a standard deviation of 10 beats per minute. What is the probability of finding somebody at Duke with a resting heart rate of 70 beats per minute or less? And what's the probability of finding a person with resting heart rate of 60 beats per minute or more? So if it's known that the resting heart rates of the Duke community is normally distributed, maybe the probability density functions of the heart rate look like this with the, again, the mean is 70, as you can see from the peak of the bell curve, and the standard deviation is 10. So from our example before, that means that 68% of the people in the Duke community, their heart rates lie within one standard deviation of the mean. So that would be either between 60 and 80. But again, it's worth noting that this distribution we have here is not a standard normal distribution, so we have to apply this Z transformation we were talking about. But to look here, it's worth noting, saying, what is the probability of finding somebody at Duke with a resting heart rate of 60 beats per minute or less, and 60 beats per minute or more? So if we look at 60 here, the area under the curve to the left of this threshold value would be the probability of getting less than 60 beats per minute, so 50, 40, 30, downward. And the probability, and the area to the right of this, under the curve of this threshold value, would be the probability of the beats per minute being greater than 60. So we're going to calculate our Z statistic, and we're particularly interested in 60. So our X value here is 60. Our mean is known as 70 beats per minute, so 60 minus 70 over our standard deviation, which is 10. And when we run that calculation, we get a Z value of -1. And so what do we do with this Z value? How do we find a probability from that? So what we do is we go to a what's called a Z table, and these are ubiquitous within statistics textbooks. And what Z tables do is give you areas under the curve for different Z values. And so you can see from up here, if you have a value Z, which is where my cursor is, the area to the left of that Z is labeled in gray. So what this tells you is for a given Z value, what the area under the curve to the left of it is. So we have a Z value of -1. So I'm going to show you how you actually read these tables. So if our Z value is -1, we go to the first column that says Z. We look down till we find -1. And these Z tables go out to the hundredths place. So we go down and find -1, and we have our Z value is -1.00. So to be more specific, -1.00. So this gives you the hundredth spot. And so we look to see where those two intersect, and it's right here at 0.1587. So what that says is that the probability on a standard normal distribution, the area under the curve, starting at -1 and going towards -infinity, is 0.1587. That also corresponds to the area under the curve for beats per minute being less than 60. So this part right here to the left, the area under the curve is 0.1587. So that means you have a 15.9% chance of finding a person with a resting heart rate of 60 beats per minute or less. Now to find what the probability of finding somebody with a resting heart rate of 60 beats per minute or more is, we would just do 1 minus that value. Since the area under the curve always sums up to 1, we could just do 1 minus that value. And in that case, it's 1 minus 0.1587, which comes out to 0.8413. So you have an 84% chance of finding somebody with a resting heart rate of 60 beats per minute or more.